that, you can look in the textbook, but let me give you a heuristic argument. So, if you substitute x equals e to the t, then that will transform a Cauchy-Euler equation into an equation with constant coefficients. And if you're interested, or you can make the substitution on your own, but the notation gets a little complicated. Okay. So let's see how the solutions to second order equations compare. Right, so what are the three cases? We could have two real. Okay, so if we have two real solutions, call them M1, M2. Then the general solution for Cauchy-Euler is what? C1 x to the M1, right? Plus C2 x to the M2. Right? So rather than making the substitution in the differential equation, let's make the substitution in the solutions. Okay, so so here it will be convenient to solve for t. Okay, so that means that t is equal to natural log of x. Okay, so we don't need to do that here. So if we replace x with e to the t, then this is C1 e to the t to the power M1, C2 e to the t to the power M2. Right, and these exponents multiply. So this is e to the M1t, C2 e to the M2t. Do I recognize this? What a solution to an equation with constant coefficients that has two distinct solutions looks like. Right, so I'm only doing this to make it believable to you that with this substitution, it's going to transform the equation. This is not a proof, but it at least shows that the types of solutions are the same. Okay, so what if we have one real? It's Cauchy-Euler, then let's call it one real solution m. So if it's Cauchy-Euler, it's C1 x to the m plus C2 x to the m multiplied by natural log x. Right, what if we make this substitution? Well then, y is equal to C1 e to the t to the power m plus C2 e to the t to the power n multiplied by natural log of e to the t. Okay, so again, this is e to the mt, C2 e to the mt. Oh, right this one. This is t, right? Times e to the mt. Okay, same type of solution that you would find if you had a repeated solution of the auxiliary equation when you have the constant coefficient differential equation. Okay, and then the last one is two complex solutions. Okay, so let's call it A plus or minus BI.
TW.
Okay, so if it's Cauchy-Euler, then the general solution C1 x to the a cosine of b natural log x plus C2 x to the a cosine of b natural log x. All right, we've done this a few times. If you substitute e to the t, this will be e to the at, right? And then log x is the same as t. Okay, so with the substitution, we get C1 e to the at cosine bt thing that we find with complex solutions, constant equations with constant coefficients. See? So, if you're interested, you can read about it in the next book, but this is only to point out that I guess at first glance, it might seem magical that all of these have solutions. You know, I mean, if you pick any random, even if they're nice looking coefficients, you're going to have a very difficult time finding a solution to a specific equation, right? This is a class of solutions with non-constant coefficients where every single one of them has a solution, and the only reason is because they're really constant equations with constant coefficients in disguise. Okay, so one last thing, I'm not sure that I'll have time for it. You have a few non-homogeneous equations in your homework. So what does it take to solve a non-homogeneous equation? All of them so far have been equal to 0, right?
Yeah, so you need a particular?
So you also need a particular solution. And in order to get the, so, you know, if you look at the example that I have, since it's equal to x squared, some careful guessing might get you at a form of the particular solution. In particular, the form is a times x squared. But it's difficult to say what you would do in general. So your safest option is to use variation of parameters. And in order to use variation of parameters, first you need to solve the associated homogeneous equation. Okay, so with these, first find yc, that will give you the y1 and the y2 for variation of parameters. Okay, then you can find the Wronskian, right? What else do you need to know? F of x, right? So you need the two solutions to the homogeneous equation. You also need f of x. Be careful with these. These are not in standard form. The f of x comes from the equation where the lead coefficient is 1. Okay, so don't forget to divide by the power of x. Okay, so I guess they're all going to be second order, so don't forget to divide by x squared. Okay, let me do this quickly. So same substitution, we'll have n minus 1, x to the n plus 10 m x to the n plus 8 x to the n equals 0. This is for yc. Okay, divide by x to the n and multiply. You get m squared plus 9m plus 8 equals 0. Okay, this factors as m plus 1. Solutions, m equals minus 1, minus 8. So this tells us, let's call this y1 and this y2. y1 equals x to the minus 1, y2 equals x to the minus 8. Okay, so this gives us the complementary function. Okay, so for the particular solution, use variation of parameters. Okay, so for this we need y1, y2, we need the Wronskian, and we need f of x. Okay, so like I said, for f of x, don't forget to divide by the coefficient. So what is f of x in this problem? 1. Right? If you divide by x squared, you get 1. Okay, so Wronskian is minus 8. times this minus this times this. So this is minus seven x to the minus ten. Okay, so you remember the formula for u1 prime.
Minus y two, that's the bags over right one.
Minus y2 f of x over the Wronski. Okay, so minus y2, so y2 is x to the minus 8. F of x is 1, Wronskian, minus 7, x to the minus 10. Okay, that makes this positive 1/7. If you bring that up, x squared. Okay, and then u2 prime is equal to y1 f of x over w. So y1 is x to the minus 1, f is 1, w is minus 7, x to the minus 10. Okay, so this is minus 1/7 x to the 9th power. Okay, so out of time, what do you do from here? Integrate these, right? And I would suggest introducing the constants. That way, when you multiply, it will give you the general solution all at once. Okay, so integrate these. Okay, and then the general solution will be u1 multiplied by y1, which is x to the minus 1. And then u2 multiplied by x, or y2, which is x to the minus 8. Okay, and I think I remember that the particular solution contribution from here and from here are of the same power, so you can combine them. Okay, so if you want, I can